Welcome back, Apologia, 8th grade, Physical Science, Week 13, Day 2, textbook pages 206 to 213, notebook pages 165 to 170. All right, acceleration. Suppose you were to throw a ball up in the air. What would happen to the ball? Well, would it go up forever, or would it eventually come back down? Obviously, it will come back down, of course. Figure 615 shows a multi-strobe photograph of one bouncing ping pong ball over time. Besides that is a diagram showing you the position of the ball at certain time intervals. Keep in mind that there are not multiple balls in figure 615. The photo shows one ping pong ball that has been bounced, and a camera took a picture of the ball every 0.05 seconds. I've included the drawing with details at 0.2 seconds so we can talk about it. Plus, the drawing eliminates the air resistance that a ping pong ball will naturally encounter as it bounces. Nevertheless, the picture of the bouncing ping pong ball gives you a clear picture of the changing position of a ball thrown or bounced up into the air. Now look closely at the drawing in the figure. The first image of the ball represents where the ball would be shortly after thrown or bounced. So right here, if it were to bounce on the ground shortly after it had bounced or hit the ground, it would be right here. The next image represents where the ball would be 0.2 seconds later. So it would have traveled here in 0.2 seconds. The next one is drawn at the position it would occupy 0.2 seconds after that, and so on. So from here to here was 0.2 seconds. From here to here was 0.2 seconds, 0.2 seconds, 0.2 seconds, 0.2 seconds, 0.2 seconds, and so on. Each image of the ball in the drawing represents the position of the ball in 0.2 second intervals. Now look at the distance between each position. The distance between the first image of the ball and the second image of the ball is fairly large. So we have this distance, and then we have this distance. The distance between the second and the third image, however, is significantly smaller. So if you look from this image to this image, even to this image, they have gotten significantly smaller. The distance between the third and the fourth images is even smaller. The distance between the fourth and fifth is smaller still, and the distance between the fifth and sixth image is the smallest. Starting at the next image, however, the distance between images begins to grow again. Well, how can this be explained? These images each represent the position of the ball 0.2 seconds after the previous image. Since the ball's position changed over each time interval, we know that it was traveling with a certain velocity. Over the first 0.2 second time interval, the ball traveled up and over to the right a certain distance. So here, it traveled up and over to the right, up, 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 over to the right. Over the next 0.2 second time interval, the ball traveled up and over to the right again, but not nearly as far. What does this tell us about the difference in the velocities between the first and second time intervals? In the first time interval, a larger distance was traveled than in the second time interval, despite the fact that each interval was 0.2 seconds. If the ball travels less distance in the second time interval, we know that the ball's velocity is lower in the second time interval than in the first. Using that same reasoning all the way up to the sixth image of the ball's velocity decreased. What happened after the sixth image of the ball? Well, by the eighth image, it is clear that the distance between the images of the ball begins to increase. This tells us that during that time, the ball's velocity increased. So we have it decreasing to here. Now the velocity is increasing to there. Thus, the ball started out with a certain velocity given to it when it was thrown or bounced. That velocity decreased until it reached the top of its path, and then the velocity started increasing again. Well, what do we call this phenomenon? We call it acceleration. Acceleration is defined as the time rate of change of an object's velocity. When an object is in motion and its velocity changes, we say that the object has experienced acceleration. You must likely have felt the effects of changing speed or acceleration. You lurch forward against your seatbelt if the car you're riding in must come to a sudden stop. If you've flown on an airplane, you get pushed back against your seat when the airplane is taking off down the runway. The acceleration of an object describes how fast the velocity is changing. Equation 6.2 is acceleration equals the final velocity minus the initial velocity over time. Like speed, we can express acceleration as a mathematical equation. Thus, the acceleration of an object can be calculated if you take the difference in its velocities over a certain time interval and divide by the number of seconds in that time interval. Let's think about the units that go along with acceleration. The units of acceleration are the units of velocity, meters per second, kilometers per hour, miles per hour, divided by a time unit. For example, meters per second per second. Well, we could just say meters per second squared. What kind of units are these? Well, we could say it was meters per second, but there is a better way to express it. Remember that a fraction merely represents a situation in which you divide the numerator by the denominator. The denominator of our unit is just seconds, but we can write that as a fraction, s over 1. An easy way to remember all of this is to memorize the saying, when dividing fractions, don't ask why, just flip the bottom and multiply. So acceleration units are read meters per second squared. Let's look at an example. All right, example 6.3. Suppose a ball is falling. A person with a radar gun measures its velocity to be 2.0 feet per second straight down. Just 0.3 seconds later, he measures the velocity again and finds that it is 11.6 feet per second straight down. What is the ball's acceleration? As always, the first thing you're going to want to do is list the information that is given to you in the problem, then list the unknown or what the velocity or what the question is asking you to find. So the initial velocity is 2.0 feet per second down. The final velocity is 11.6 feet per second down over a time period of 0.3 seconds. So we need to figure out what the acceleration is. Step 2, write out the equation you're going to use. So we're going to use acceleration is final velocity minus initial velocity divided by time. Step 3, substitute the numbers in from up here. So we have final velocity, 11.6 feet per second minus initial velocity, 2 feet per second divided by 0.3 seconds. So we solved the problem. The acceleration can be expressed as 32 feet per second squared downward. The units on acceleration then are a distance unit divided by a time unit squared. Thus, units like feet per second squared, meters per second squared, or miles per hour squared, and kilometers per minute squared are all valid acceleration units. Did you notice that directional information was included in the answer to example 6.3? And that's because, like velocity, acceleration is a vector quantity. How do you attach directional information to acceleration? In order to determine the direction of acceleration, you need to know the direction of the velocity, and you need to know whether velocity is increasing or decreasing. Remember, acceleration is the change in velocity. And velocity can change in one of three ways. The first way, if an object speeds up, obviously the velocity changes. If an object slows down, obviously the velocity changes. Finally, if an object changes direction, the velocity changes. Also remember that velocity is a vector quantity. Thus, direction is part of velocity. Even if an object's speed does not change, if its direction changes, its velocity changes. In all three of these cases, then, there is an acceleration because there is a change in velocity. We can determine the direction of the acceleration if we examine how the velocity is changing. For example, suppose a car is heading west and begins to increase speed. The car is accelerating, but in what direction? Well, since the westward velocity is getting larger, the change in velocity results in more westward movement. Thus, the acceleration must have a direction of west. Suppose that the car began slowing down. What's the direction of acceleration then? Well, if the westward velocity decreases, that means the acceleration is going against the velocity. Thus, the acceleration's direction is east. If an object is speeding up, then its acceleration is in the same direction as its velocity. If it is slowing down, its acceleration is in the opposite direction as its velocity. All right, that might be a little confusing, so let's see how that works in example 6.4a. A rock is dropped from a bridge into a river. It starts out with 0 initial velocity and it hits the river 2 seconds later, traveling with a velocity of 19.6 meters per second downward. What is the acceleration? All right, step 1, always list the information that's given. The initial velocity is 0 meters per second. The final velocity is 19.6 meters per second down. The time is 2 seconds. We need to figure out what the acceleration is. So step 2, write the equation that you're going to use. So we're going to use the same one we've been using. Acceleration is the final velocity minus the initial velocity divided by time. Write out the equation, substituting the numbers in. So the final velocity was 19.6. The initial velocity was 0 divided by 2. So then when we solve the problem, we get 9.8 meters per second squared. The rock sped up because it started at 0 and ended traveling 19.6 meters per second downward. Thus, the acceleration must be in the same direction as the velocity. Therefore, the acceleration is 9.8 meters per second. You must have downward in your answer. Let's go on. A bicyclist is traveling down a road at 18 feet per second to the east. The cyclist sees an obstacle in the road ahead, so he hits the brakes. In 1.8 seconds, the cyclist has come to a complete stop. What is the cyclist's acceleration? All right, obviously, step 1, list the information that is given to you. We have the initial velocity as 18 feet per second east. The final velocity comes to a complete stop. So obviously 0 feet per second. It took him 1.8 seconds. So we have to solve for acceleration. We use the same equation that we've been using. Write out the equation. Acceleration equals final velocity minus initial velocity divided by time. Step 3, substitute in the numbers from up here. And then step 4, solve the problem. So we get negative 10 feet per second squared. Well, what does that answer mean? When we subtracted 18 from 0, we got negative 18. When we divided that number by 1.8, the negative sign stayed around. What does a negative acceleration mean? Well, it tells you about the direction of the acceleration. The bicyclist slowed down. That means that acceleration is in the opposite direction as the velocity. That's what the negative sign means. It is reminding you that the cyclist slowed down, making the acceleration opposite of the velocity. Since the velocity's direction is east, the direction of the acceleration must be to the west. Therefore, the acceleration is 10 feet per second squared west. Now notice how I dropped that negative sign. Well, the negative sign helped me determine the direction of the acceleration. Thus, I didn't really drop the negative. I just turned it into the direction. And that's what you should do as well. If you come across a negative acceleration, you should use that negative to help you determine the direction. But only the direction should show up in your answer. All right. Before we move on, there are a few more points about acceleration I want to discuss. We saw in the second problem of exercise 6.4 that acceleration can be negative. This happens when velocity decreases, which means that the object is slowing down, which makes the numerator of equation 6.2 negative. Some people use the term deceleration to describe acceleration that slows the speed of an object. Although that is an accepted term in everyday English, it is not an acceptable term in physics. When we talk about acceleration that slows an object down, we do not say deceleration. Instead, we give the direction of the acceleration. When compared to the direction of the velocity, the acceleration's direction tells a physicist whether an object slows down or speeds up. In the end, then, when you read acceleration, do not assume it means that an object is speeding up. Acceleration can either speed up or slow down an object, depending on its direction. All right, that brings me to my second point. You know that acceleration means a change in an object's velocity over time. But did you know an object can have constant speed and still have acceleration? Well, how is that even possible? Look at the carousel in figure 616. I didn't put a picture for you to see. Just imagine a merry-go-round or a carousel. Riders on the carousel experience a constant speed, but since the carousel is continually changing directions, the riders also experience acceleration. Because remember that acceleration and velocity are both vector quantities. Thus, if an object moving at a constant speed changes its direction of travel, such as that carousel or merry-go-round going in a circle, there is still acceleration. Of course, you can have changes in both speed and direction. You experience this type of motion if you ride on roller coasters. A roller coaster car whips you backward, forward, and sideways as its velocity increases, decreases, and changes direction. The thrill you experience riding a roller coaster comes from the constantly changing acceleration, changes in both speed and direction. My last point is a reminder about units when solving acceleration problems. In order to properly do the math using equation 6.2, you must make sure that all of your units agree with each other. And what do I mean by that? You should not have hours and seconds in the same equation, nor should you have feet and miles in the same equation. You shouldn't have millimeters and centimeters in the same equation. Every unit for length should be the same, and every unit of time should be the same. You must always remember to convert one of the two different quantities. All right, so the next two examples are going to help us learn this. All right. Example 6.5. A sports car travels from 0 to 60 miles per hour north in 6.1 seconds. What is its acceleration? All right, 1A. List the information. Initial velocity, 0 miles per hour. Final velocity, 60 miles per hour north. The time, 6.1 seconds. All right. Step 1B. You should have noticed right away that we have an answer in seconds and we have an answer in hours. So you need to convert. In most cases, you should convert whichever is easiest. And for this problem, convert 6.1 seconds to hours, where 1 hour equals 3,600 seconds. So 6.1 seconds times 1 hour over 3,600 seconds equals 0.00169 hours. All right, step 2, write the equation you will use. It's the same acceleration formula we've been using. Step 3, substitute the numbers in. And then step 4, solve the problem. All right, 35,503 miles per hour squared. That's a big number. Since the car's speed increased, the acceleration and velocity have the same direction. Therefore, the acceleration is 35,503 miles per hour squared north. When looking at a physics problem, you must follow the steps for solving problems. 1. First, write down your knowns, the values given in the problem, and the unknown, what the question is asking you to find. And remember to include units. I would also like to add, sometimes a picture is very helpful. Step 2, check to make sure all the units agree. If they don't, you'll need to convert some units into the other for agreement. Step 3, next you need to figure out the equation that you're going to use. Step 4, determine where the values you listed in step 1 fit into the equation and write the equation with the listed values. Step 5, finally, solve the problem. All right, on your own, 6.9. A child is sledding. He starts at the top of the hill with a velocity of 0. 3 seconds later, he's speeding down the hill at 12 meters per second. What is the child's acceleration? All right, we listed what we know. We're trying to find the acceleration. We are using the same equation that we've been using. The divided sign should be here. So the final velocity minus the initial velocity divided by time. Step 3, we substituted our numbers in from step 1. And step 4, we solved the problem. 4 meters per second squared. The sled's velocity increased, so the acceleration has the same direction as the velocity. Thus, the acceleration is 4 meters per second squared down the hill. On your own 610, once that same child reached the bottom of the hill, the sled coasts for over a long flat section of snow. If the child's velocity when the sled starts coasting is 12 meters per second east, and the child coasts for 6 seconds before coming to a halt, what is the child's acceleration? All right, so we listed the information that we know. Write out the equation that we're going to use. Once again, the line should be under here. The final velocity minus the initial velocity over time. We substituted in our unknowns or what we know from step 1, 0 minus 12 meters per second over the time of 6 seconds. That is going to give us a negative sign. So remember what that negative sign tells us. It tells us that the acceleration is in the opposite direction as the velocity. And this really does make sense since the sled is slowed down. Since the negative sign tells us about direction, we drop it from the answer and replace it with the actual direction. So it was initially told us going east. Well, once we have that negative sign, we're going to change it to the opposite direction or west. The last one, 6.11, a good runner can keep up a pace at 0.15 miles per minute for quite some time if a runner starts from rest and settles into a velocity of 0.15 miles per minute south. After 3 seconds of running, what is the runner's acceleration over that 3-second interval? Once again, same thing. We list the information that we have, and then we realize that we're going to have to do some converting because we have seconds and we have minutes. So we're going to want to convert into minutes. So 3 seconds equals 0.05 minutes. We're going to write the equation that we're going to use. Once again, this should have had a divided by sign. Step 3, write out the equation, substituting the numbers from the list in steps 1A and 1B. So here we go. And then solve the problem. We have 3 miles per minute squared. Since the runner sped up, the acceleration and velocity are in the same direction. Thus, the acceleration really is 3 miles per minute squared south.